So then what is it that makes this ozone hole appear around the South Pole, but maybe not around the North Pole? And what is it that really causes this ozone hole to appear? Well, it's catalytic destruction of ozone by primarily chlorine in the atmosphere. As we mentioned in chapter 1, there's several other agents, bromine as well, that can be involved in ozone destruction. But chlorine is the primary culprit, partially due to its concentration being higher than bromine in the stratosphere, and to a number of chemicals that we'll get to later that have been emitted into the atmosphere that make its way up into the stratosphere and then produce chlorine on the atomic chlorine, much more than bromine, and just the simple effectiveness of chlorine at ozone destruction. But wait a moment, you might be asking, I thought about 99% of the chlorine exists in its inactive form, HCl or this chlorine nitrate. So why is 1% chlorine really an issue? Well, it might not actually be much of an issue if the chlorine existed in its inactive form all year round, but it doesn't. There's this period of time that requires specific conditions where the inactive chlorine gets converted into active chlorine. And that occurs during the Antarctic winter. So when the sun sets and does not rise again for about 3 months in the during the Antarctic winter, we have several things occur. The temperature drops dramatically. We get down to about -80 degrees Celsius. And there's also the formation of a polar vortex with these really cold temperatures. You will get this spinning, combine the very cold temperatures with the Earth's kind of rotation, and we get this spinning vortex around the South Pole that has wind speeds up to about 120 miles per hour or more. And what it results in is that the air inside the vortex is isolated from the rest of the atmosphere. And there's no matter that's really able to get inside the vortex during that time. And what that means is that there's no mixture of components from air outside that vortex that would reestablish any kind of equilibrium that is thrown off by reactions that occur in that vortex. Now, although around the South Pole there's not a lot of humidity, it's generally not a lot of water in the atmosphere, and particularly in the stratosphere, but when the temperature drops all the way below or to -80, it's cold enough that it starts to form particles by condensation of what little water vapor there is, with also nitric acid as well. And we start to form these polar stratospheric clouds, which are composed of particles that are primarily ice particles with some nitric acid. And on these water and nitric acid crystals in these polar stratospheric clouds, these catalyze the activation of inactive chlorine, and it occurs through several reactions. So first, the chlorine nitrate, which is perhaps the main form of inactive chlorine, it will come, and on the surface of that particle, where there's a small layer of liquid water on the ice particle, the chlorine nitrate will essentially react with that water to form HOCl, and essentially that's hypochlorous acid, and nitric acid, both on the surface of that particle. Then the other form of inactive chlorine, which is HCl, will also essentially come and react with that water layer on the particle. And then just like HCl does in normal aqueous conditions, it will dissociate into its ions. The strong acid, so you get the H+ ion and the Cl- anion. Now, if you've got a Cl- anion and you've got a very reactive hypochlorous acid here, Cl- will react with the Cl and hypochlorous acid to form molecular chlorine, or diatomic chlorine, plus the hydroxide ion. And that hydroxide ion then just goes and recombines with the H+ ion from HCl to reform water. And we've generated then an equivalent of chlorine gas, which is released from the particle. If we take all of these four reactions, we sort of sum them together, we can get this net reaction, which is just the reaction between the two inactive forms of chlorine, the chlorine nitrate and HCl, hydrochloric acid, to form diatomic chlorine and nitric acid. That diatomic chlorine is released from the particle. This is sort of illustrated in this figure in your textbook, where we have that crystal with an aqueous layer on it, and then HCl adds, HCl kind of gets dissolved in that and then reacts with the chlorine nitrate through various sequences as we sort of went through to generate chlorine gas. So this occurs all winter long. These particles, these polar stratospheric clouds form particles. That takes the inactive forms, both inactive forms of chlorine, and converts them both to molecular chlorine gas. And then early spring rolls around and the sun rises again, and we still have extremely low temperatures. The polar vortex stays in place for probably a couple months through most of the spring. And so we still have inactivation or activation of the chlorine from any of its inactive forms. But the sunlight now dissociates the molecular chlorine into two equivalents of atomic chlorine. And then that atomic chlorine is able to go on and act as an ozone destructive agent. Also, any of the hypochlorous acid that happens to be released from the particle also is dissociated by sunlight to generate an equivalent of atomic chlorine. Now, normally, that atomic chlorine, the main sink for it in the stratosphere is reaction with NO2 to form the chlorine nitrate. But the NO2, all of the nitrogen, is sequestered in the polar stratospheric clouds in these particles as nitric acid. And the heavy particles fall down just by the force of gravity, fall down out of the stratosphere into the troposphere. And that results essentially in the removal of nitrogen, or the denitrification of the stratosphere. So now when early spring rolls around, we generate large amounts of active chlorine, the atomic chlorine, but there's no or very little NO2 or nitrogen dioxide to react with that active form to deactivate it now. So now the chlorine has gone from 99% inactive to 99% active in the stratosphere. And this results then in ozone destruction on a massive scale, resulting in the ozone hole. Now, the actual mechanism for ozone destruction follows primarily mechanism 2, if we're talking about the lower to mid stratosphere where the ozone layer exists. And so we have chlorine reacting with ozone to generate the chlorine monoxide and O2. And then that ClO gets turned back over to atomic chlorine through a sequence of reactions. So we take two of those ClO groups, combine them together to form dichloroperoxide. And then this dichloroperoxide, similarly to what we talked about in chapter 1, will undergo decomposition. But we need a little bit more details here in terms of how that happens. So this is actually a photolysis process. The dichloroperoxide absorbs UV light to dissociate one chlorine atom. So you break one oxygen-chlorine bond. And then the remaining ClOO absorbs another photon of UV light to dissociate the other chlorine atom and leave you with molecular oxygen. If we sum reactions 2A through 2C, we get what we're more familiar with, which is just essentially the conversion of the chlorine monoxide back into atomic chlorine, just kind of returning over the catalytic cycle and regenerating the active ozone destructing agent. But there are a few notes to make with this. There's some requirements with this, particularly the second set of reactions. So the first is that this, in order for the chlorine monoxide to be turned back over into atomic chlorine, this requires that we maintain very cold temperatures, so down around the -80 again. And the reason for that is that this dissociation reaction is a bit of an equilibrium. It is exothermic, but it's not hugely exothermic. And so if, well, with warm temperatures, it tends to dissociate simply the oxygen-oxygen bond to regenerate two equivalents of the chlorine monoxide, which then is just kind of stuck. It can't destroy ozone by itself. It really needs to be turned over into atomic chlorine and release O2 in order to be able to do this. And then the second part is that this does require appreciable light intensity. So probably maximum ozone destruction occurs not at the very beginning of the springtime, but a little bit later into the spring, because 2B and 2C both require UV light, and additionally, the desired reaction which is shown is not the only reaction that occurs when dichloropyroxide absorbs UV light. Another reaction is simply the dissociation of the oxygen-oxygen bond to regenerate to equivalents of the chlorine monoxide. So we do require at least a certain level of UV intensity in order to turn this back over to atomic chlorine. And then the last part in this process, or last thing to note, or part of the last kind of contributing factor here, is that 2A is actually the rate limiting step of this sequence and of the entire ozone destructing sequence, or ozone destruction destroying sequence. The reason for that is if we draw out the rate law, we can see there's two equivalents or two molecules of ClO involved, and so our rate is not just dependent, it's not a first order dependence on the concentration of chlorine monoxide, it's a second order dependence, which gives you this quadratic dependence then on the concentration of ClO, which then, of course, since we need two of them and it's doubly dependent on the concentration, the concentrations initially at least would be low, then affects the overall rate of this reaction, making this the slow step. What falls out of all of this, if you're following with me, what comes out of all of this is that in this sequence, this catalytic cycle of taking atomic chlorine, destroying ozone to get to chlorine monoxide, and then regenerating the atomic chlorine, in this whole cycle, chlorine monoxide is the resting state. It's because the turning back over of that chlorine monoxide is the slow step, then the catalytically active chlorine exists more in the chlorine monoxide state. So in this cycle, this is sort of the resting state. And we can see, if we take that information and measure the concentration of ClO, what we see then is that there's a really nice anti-correlation between the concentration of ClO and the concentration of ozone as we move, as we change latitude. So here, what we'll notice if we look at this graph is that when we're not near the polar region, so remember the South Pole is at 90 degrees south. So when we're far away from that, then we are outside the vortex and we don't have these particular conditions that are very specific to the formation of active chlorine. So chlorine exists primarily in its inactive form, and we don't see a lot of ozone destruction. And so there's a concentration of ozone, and we can still measure the concentration of ClO. That would be fairly low. But then what we notice is that as we get closer to that polar vortex and kind of enter it, we see then this really nice anti-correlation between the concentration of ozone, which drops off, and the concentration of ClO, which we can measure as the primary form at any given moment of chlorine during this ozone destroying sequence, or during destroying time in the springtime in the southern hemisphere. So then once we've got got these active form of chlorine, it goes on and destroys ozone on a massive scale, opening up the ozone hole during the early and late spring and into the summer months in the southern hemisphere. But then eventually the hole closes again. So how exactly does that occur? Well, what happens is in the late spring and really into the summer of the southern hemisphere, the temperature starts to increase. And so once we get up above about -80 degrees C, the polar stratospheric clouds start to dissolve. Those particles melt again, and also the polar vortex begins to disappear as well, since we don't have the frigidly cold air temperature anymore. That results in a few things. One is that nitric acid is now released from those particles as they kind of dissolve into the atmosphere. And the nitric acid that is released now undergoes photolysis by absorption of light to regenerate nitrogen dioxide and a hydroxyl radical. And that nitrogen dioxide, which is now being reproduced in the stratosphere, then reacts with atomic chlorine or with chlorine monoxide to deactivate it and pull the chlorine into its inactive form. More importantly, though, even than that, is the fact that the polar vortex has disappeared. And when the polar vortex disappears, then you're able to have air mixing from the polar region with the other non-polar regions. And that mixing of air brings in more nitrogen dioxide, which then reacts with the chlorine monoxide to deactivate it. So you've got both of these sequences going on here. You've got the release of nitric acid and then photolysis to generate nitrogen dioxide, which then reacts with chlorine monoxide to deactivate it. And then you've also got the mixing of normal air with its normal NO2 concentration with the polar air, and then that also deactivates the chlorine monoxide. And so as you get into the late spring and into the early summer, then we have an increase in the concentration of NO2, which leads in a decrease in the concentration of active chlorine. What happens after the chlorine has returned to its inactive form is that the ozone layer slowly auto-repairs. So we have the normal formation of ozone, which involves dissociation of O2, the two oxygen atoms. Those combine with O2 to reform ozone. And then slowly that ozone concentration will build up until it reaches a steady state concentration. So at some point, we increase the concentration of ozone to the point where eventually the normal destruction processes that occur in the Chapman cycle, as well as some of the catalytic processes for ozone destruction that occur even with, say, the 1% of chlorine that's remaining, or a couple of the other more minor catalytic ozone destroying agents, such as hydroxide or hydroxyl radical or nitric oxide. Those eventually we reach this state where the formation of ozone, that rate is now equal to the rates of the destruction of ozone, and then we've reached a steady state concentration. And we can see that by about January or so, we've reformed most of the depleted ozone. Now, why do we spend all this time talking about the ozone hole? What's kind of the significance of it? Well, one major significance is that when the ozone layer is depleted, there's no longer anything in the stratosphere or the troposphere to filter out the UVB light. And that UVB light we're concerned about because it overlaps with the absorption spectrum of DNA. It can result in melanomas and skin cancer, and some of those can be fatal. And there's a few examples of this. You might wonder, well, why, okay, it's over the South Pole, but nobody lives at the South Pole, so maybe that's not that big of an issue. But it really extends a little bit beyond that region. And so here's one example of just the ozone hole in 2009. You can see it's reaching all the way to the end of South America. So Tierra del Fuego in South America experienced for a few weeks a significant increase in the amount of UVB light due to this ozone hole that stretched over that region. And then we haven't really talked that much about the northern hemisphere and the North Pole ozone holes. But occasionally some ozone holes have opened over the northern hemisphere, and in 2011 there was an increase, an ozone hole kind of over Finland, and that certainly exposed those people to an increase in UVB light, and particularly for Northern Europeans that have very light skin, skin cancer due to exposure to UVB light is a major concern. Now, we'll pause right here and talk for a moment about why does the North Pole not have the same polar ozone hole as the South Pole does? Well, it's due to a couple reasons. One is with the Himalayas throughout Europe and kind of northern Europe, the Himalayas stretch so high into the atmosphere that air coming up off of them actually is carried up into the stratosphere, and that air is warmer than the normal stratospheric air, and it warms the stratosphere during the winter months. And so we don't get to the same level of extreme temperatures that are required for the formation of the polar stratospheric clouds. Now, it doesn't mean that it doesn't happen, but it doesn't tend to happen as much. And even though we do reach extreme temperatures in the Arctic, because of that warm air that rises, often the cold temperatures don't last entirely through the winter. And so by early spring, you're starting to have some temperature increases that result in the decrease or dissipation of those polar stratospheric clouds, and then the deactivation of any chlorine that had been activated during that time before you get enough light intensity in early spring to really cause the massive levels of ozone destruction that we see in the south. And so that kind of region, we don't see the same level of the polar vortex either in the North Pole, around the North Pole, as we do around the South Pole, and that has to do simply with geological features. And because of that, you can also have air mixing to some degree, especially in the really late winter and early spring, that results in the deactivation of any active chlorine. And so although some years, depending on the particular conditions, you will see ozone holes open over the Arctic, it's really never to the extent that we see over the Antarctic. Now, back to this ground level UVB exposure. So Finland, okay, one year there was a problem in the lower portions of South America. Maybe that doesn't seem like too much of a problem to us here in the United States, but really it stretches beyond that. So New Zealand is a classic example, and Australia is also really a classic example of this. In the 1990s, what they noticed simply measuring was that over a single decade, they had a 12% increase in ground level UVB intensity. And they actually published this in a science paper where you notice that they kind of plot the average ozone levels in Dobson units here, and you can see this decrease, even though New Zealand is a little ways away from the South Pole. It's certainly not, and Australia as well, but both are extremely relevant areas, and this chemistry is extremely relevant to the populations of those areas. And so you see this significant increase in UVB light over only about a decade. Now, what results from that is that New Zealand has the second highest rate of skin cancer in the world, and it's only second behind Australia, also in a similar region of the Earth, near that polar ozone hole. And this is directly linked to the increase in UVB light that results from ozone depletion. So those are both extremely relevant examples of where this plays a big part in the role of everyday people's lives. And we might talk a little bit about this more in some of the subsequent videos, but it's not only polar regions that experience ozone depletion, there's also ozone depletion that occurs in the mid-latitude regions as well and over North America. We simply don't see the same massive scale of ozone depletion as we see over the South Pole.